Okay, today we are going to learn how to obtain numerical solution of an ordinary differential equation. First, let's define that what type of the equations are known as differential equation. Answer of this question will be an equation which contains independent variable, dependent variable, and derivatives of the dependent variable is known as differential equation. An ordinary differential equation contains only first derivative along with independent and dependent variables. The general form of the ordinary differential equation is written as dy upon dx is equal to fxy. Solution of this differential equation can be obtained only in that case when one initial condition is known. For example, value of dependent variables corresponding to independent variables at x is equal to x0, let's say it is y0. The previous equation dy upon dx equal to fxy can be rewritten as dy is equal to fxy dy. Now integrating both sides from x0 to x1, we find integration from x0 to x of dy equal to x0 to x of fxy dx, or it can be written as yx minus yx0 equal to integration from x0 to x fxy dx, or yx is equal to y0, where y0 is corresponding to initial value of x, that is initial condition, plus second term value x0 to x fxy and dx, integration of. The second term of the above equation is to be determined. Numerically, this approximate value is obtained. Now we will discuss about one of the classical method known as Euler's method to find the approximate value of this second part. Euler's method. Question: obtain numerical solution of y corresponding to given x in differential equation dy upon dx is equal to fxy. Initial condition is y x0 is equal to y0. This is problem and we have to find solution to this particular question. Approach. What will be our approach? If in this particular case, if x is far away from x0, then region between x0 and x is divided into n parts. The solution is obtained starting from initial point and moving towards our point of interest as follows. Let different points in the interval x0 and x are known as x1, x2, x3 up to xn minus 1, and the last point is known as xn. Integrating differential equation between limit x0 and x, the value of y at x1 is obtained solving yx1 differential equation, above differential equation, yx1 equal to yx0 plus integration from x0 to x1 of fxy dx. If we assume that the value of y is almost same between the value of second term, can be approximated treating fxy as constant fxy. Thus, we can write above equation as yx1 equal to yx0 plus fx0y0, which is taken outside because it's treated as constant, taken as constant, and integration from limit x0 to x1 of 1 with respect to dx. This implies that we have obtained the value of y at x1 from the initial value of y at x0. In this way, if we consider yx1 as initial value for second interval, that is from x1 to x2, the value of y at x2 will be yx2 is equal to yx1 plus yx1 y1 h, and yx3 is equal to yx2 plus f x2 y2 into h. Thus, at the end of ith step means interval, general form of the equation is written as yxi is equal to yxi plus f of xi minus 1 yi minus 1 into step size h. What are drawbacks of this Euler's equation? Because in this particular case we considered gradient of dependent variable as constant at every point in one particular interval. Therefore, this assumption adds error in the final result. Here, this is algorithm which we can write or use to solve any given problem. The very first statement which we use to write when we write any algorithm is that what can be done with that particular algorithm and what are knowns. So I have written here, this algorithm provides solution of differential equation dy upon dx is equal to fxy. The initial condition value or condition of y at x equal to x0 is y0. Step first should be to read the initial value of x and y as are in the name x0 and y0. Second step, read last value of x as x1, xn. Step 3, read number of intervals n. Calculate step size h is equal to xn minus x0 divided by n. Now just use a loop to calculate value of y at a different point. In this way, for I equal to 1 to n, now corresponding to any ith point, we can write this formula yi is equal to yi minus 1 plus function corresponding to I minus 1th point into h. Now, xi is to be, of course, upgraded, means move one step ahead. So it will be xi minus 1 plus h. Now, when we print xi minus 1, yi minus 1, then we find information about different values. Here I think it will be better if I do this one, because we have to move first point onward. Value of at first point is already known, therefore second point onward, because loop starts from I is equal to 1 to so on. So first time value of I will be equal to 1, therefore in this statement it will be y1 equal to y0 plus f x0 y0 into h, and next time x will be equal to x0 plus h, means x1. Second time when I will be equal to 2, it will be y2, and the value of y which we take as initial value, that is equal to yi minus 1 plus y xi minus 1 y x1 y1 into h, and so on.